Sure, in thermo, he showed it to us.
Wait, do you want me to turn it sideways or vertical?
He moved them. Like, did you
Whichever
particle in a
fits
box,
the-
which is relevant in
I
what
think I can see it okay. Here, this is what.
Fine.
Okay. There we go.
Alright, just before I go into like the just before I go into more computational stuff, do you guys know like what the background for this paper? Like,
Yeah, you're good.
yeah, or
I think so.
What do you mean by background?
like what's actually happening? Like, what kind of problem are we looking into? So like similar to lithium like metal ion batteries, the biggest problem is the dendrite growth. When you charge the battery, the anion that was transported to the cathode, when it comes back to the anode, it doesn't necessarily diffuse in a form where a horizontal surface is going to form. So just to give you a brief idea, this is not what should be drawn in the exam, but let's say that's zinc. And an ion comes off, goes off to cathode. And there's going to be that part where the anion came off from. When it comes back onto the surface, when you charge it, it's not going to go back into that original space. It's going to fill in, it's going to be attached to anywhere that's energetically favorable, which is a problem. When another one comes back on, it's going to be diffused onto this tip, essentially growing into a branch-like structure, where it will keep on growing, cut through the separator, and eventually could potentially touch the cathode, and battery is ruined. And this is like the major problem. And what we're trying to do is coat this material of VSE2, and this could essentially lead to a better deposition of ions, where it is more horizontally stacked rather than a branch-like structure. And you want to see why with the computational work? Okay, so going back to DFT, that is a many-body Schrodinger equation. This small r represents electron. The big R is the nucleus. And this is where the first approximation comes in, which is the Born-Oppenheimer approximation, which is pretty much saying that nucleus is super heavy and the movement's gonna be really slow, whereas the electron is gonna be the opposite, light and fast. So from that, we could separate this equation into two parts, which is the nucleus and the electron. Does that make sense? So now, when we look at the computational study, we can only solve for electron because electron is the thing that determines the physical properties, how it's going to behave, most of it. The nucleus, we can just not think about it. Okay, so that's one step into computational, just trying to look at the electron. So that's great. However, for example, if you want to solve the structure for CO2, let's say, and in the molecule there are 22 electrons, and if you look at the three dimensions for each electron, there are 66 dimensions that you have to solve, which is insane. The computer just cannot do that. So this is where the DFT comes in. Now you guys don't even need to think about this. So DFT is a density functional theory, and as you can tell from the name, there's this Hartree product approximation as well, but you don't need to know that. So DFT just treats these electrons, let's say they're in a circle, as not a single electron, but one cloud of electron density. And that's why this calculation is somewhat doable. So, yeah.
Yes.
So far, that's that. So pretty much this went from one many electron to many one electron. And this, now we only have to look into 3 dimensions of one big electron, if that kind of makes sense. Now that's where the computational burden decreased by insane amounts. So one thing I also want to mention, I said he might be asking about the difference between DFT and MD, which I'll go through later on, but before, I think you guys need to know about ab initio. So ab initio was pretty much solving the Schrodinger equation that I just wrote down. So ab initio, just by the word itself, means first principle. So this is a method. So this method came out from scientists where they thought, just by knowing the atom and the number of electrons, we want to know its structural properties, mechanical properties. So just by looking at that, that's the method called ab initio, which is also based on quantum mechanics. But the difference between DFT and ab initio is that ab initio does not use any empirical formulas or any assumptions, just by looking at the electron and the nucleus. But as you just saw, DFT kind of transformed all these electrons into one cloud of electron. So the big difference is that ab initio is solving the pure wave equation that I just wrote down, the Schrodinger equation, whereas DFT is solving for the electron density. So you can kind of say that DFT came about from the process of trying to solve for ab initio, but ab initio is pretty much almost impossible to do so because of the things I just mentioned. For example, 22 electrons give you 66 dimensions and everything. So yeah, that's the difference. Okay, so one thing. So later on, when you solve for DFT, okay, so now we're trying to solve for the energy density of a molecule, where the molecule is at its lowest stable state possible. And when you try to solve for the energy, this is what you get. So some parts of the equations are known. For example, in this part, electron velocity, the repulsion between electrons, the repulsion between electron and nucleus, the attraction between nucleus and electron, all those are included here. And this part, I'm not sure if you need to know, but this was kind of in the paper, so I'm just gonna go through real quick. So there's this part of the equation where we don't know how to define it, but we know it kind of exists. So we have to make an approximation for it. And those are called exchange correlation of functional. And from the name DFT, density functional theory, the functional means equations of equation. So Yeah, so set of equations. Yeah. So just to tell you, this is an approximation. And there are two types of approximations, which is LDA, GGA.
Which one is the approximation?
Oh, this part.
The exchange?
Yeah. This is all the known parts, like the relation between nucleus, electron, nucleus, or anything. Yeah. So, but don't dwell on this too much. I'm just gonna go through. LDA is local density approximation, whereas GGA is the generalized gradient approximation. And if you see from the paper, this is what all the computational papers are gonna look like. When they, on the second page, when they start talking about DFT, lower right, we have to talk about all the parameters and all the settings that we have. And this is just pretty much one of the settings that we assumed. So for example, in my computation, I'm gonna use LDA approximation. In my computation, I'm gonna use GGA. That's pretty much what it is. And here they say, actually, they don't. I know on paper 13 says it on
Yeah.
the
Are they
GGA or
something
anything.
else
Yeah.
on, page 3?
Page 3?
Yeah, like half paragraph on the right, they say DFT D3 correction. I think it's along the same lines.
That's something kind of different, but
Oh yeah, that's between the functional layer and zinc. Yeah.
yeah. Okay, so DFT, that's pretty much all the basics. That's it. And I'll just go through some of the concepts that they showed on the paper. The first one's a cutoff energy. So, are you guys all familiar with reciprocal space? Mm-hmm. Like from crystals? So like even from XRD, you're looking at the reciprocal space. So since DFT is also solving for wave functions, essentially, we have to look into reciprocal space. And when you solve for these wave functions, the Fourier series comes in, which is don't panic. It's just solving for sinusoidal equations. And it's just that they are gonna converge and they're just gonna expand. And at some point, because the computer's gonna explode, we have to tell the computer, just stop at this point. That's the cutoff energy. And they're gonna say that the cutoff energy was 500 eV. That's it. So that comes from the concept of reciprocal space and Fourier series expansion. K-point sampling is, so when you look at the reciprocal space, and in the real space, if the molecule is small, in the reciprocal space, it's gonna be big. In the real space, if it's gonna be big, it's gonna be small in the reciprocal space. And the Brillouin zone, called in short BZ, that is a conceptual kind of thing. It's a primitive cell in the reciprocal space. And the K points are just some of these random points that you're going to choose from that primitive cell in reciprocal space, which is Brillouin zone. And then you take the average of these points, because you can't really analyze the entire thing. We're just trying to take some samples of each point and see and average it to kind of do the calculation. But no detail needed. Okay, very last thing on DFT. Pseudopotential is, so as I mentioned earlier, all the chemical bonding and most of the characteristics are defined by the outer shell of electrons, like 2, 8, 1, but the one's like the one that's kind of important. So here, because we essentially try to lower the burden and cost of computation. Pseudo potential is pretty much, let's say, here's one. And we don't calculate the entire thing. The pseudo potential is a one function that just gives you an approximation of this part. So we only have to focus on this electron. So pseudo potential is pretty much a fake potential that's gonna approximately represent this core part of the electron. That's not gonna play that much of a role. Yeah.
So basically the pseudopotential simplifies the inner part of an atom so that we can focus only on the outer shell?
Yes.
Okay.
That's it. Yeah. So that's all the things I need to tell you about DFT. So here, as I mentioned, DFT tells you the lowest energy state in a system and the binding energy. So here, this concept came in because if you look at the, let's say that's zinc. Let's say that is medium saline, and there's zinc 2+ ion coming in. So what we want is we want the zinc ion to be diffused to this material rather than zinc. So they experimentally already showed that the TM and XRD all comes in from showing that from experimental work, it all worked just fine. Like it all showed a very horizontal growth, and this worked out. But since we want to show that, like computationally show that this is actually gonna bind to this instead of this, DFT comes in. We calculate the binding energy between zinc and compared to zinc. And if the binding energy between these two, if this is larger, that is going to be favored when this comes into the system. So, but when I say larger, I mean it in a magnitude manner. So if you see from the abstract, there's a higher zinc adsorption on VSC rather than onto the zinc. By comparing to negative 0.54 to negative 0.48. Yeah, so from DFT we show that this is favored. That's why DFT comes in. That's the whole thing. So that's the DFT part. And okay, molecular dynamics. Are we good to move on to molecular dynamics? Any questions yet?
I do have a question. For the methods in this paper, on page 2, it talks about FASP.
Yeah.
And then the PAW, that's the pseudopotential thing. But what's the VASP mean?
So VASP is, DFT is a method of solving, and this is the method, and that's a software. So this is the name of the software.
It's just the name of the software. It's
So-
still the ab initio thing that we're talking.
Yeah.
Okay.
So
Interesting.
DFT can be solved on different softwares. First is FASIP. Second is Quantum Espresso. Third, another software. There's a lot of softwares, but
Okay.
here they're just telling you which software they used. That's it.
Could you also explain the Brilliant Zone again?
Yeah, so the Brillouin zone is the primitive cell in the reciprocal space.
Okay.
So we cannot solve the real space. We have to solve the reciprocal space, and that's just a primitive cell in the reciprocal space.
Okay.
Yeah, and the K points are the random points on the primitive cell that we're gonna take an average for calculation. Yeah.
I have a question.
Yeah.
I guess there's still a little bit of a disconnect in my mind how we got all the theory of like which numbers or which parameters we're selecting, and then how we land on these binding energies. Like, is it just put that all into the simulation and then it spits out those binding energies back at us? Are we supposed to know from how we got from A to B?
Right. So how should I explain this? Just to give you an idea how computation works. For example, let's say we want to test for zinc metal and this H2O water, and we want to see on the zinc surface, we want to see which direction or the formation of water molecule is the most stable and energetically favorable. And first, we are gonna give appropriate forces that are being applied, and then we run the simulation, and then the results are gonna be showing you how the H2O is oriented on the surface, which is the most stable, and it will tell you the binding energy between the two, and that's what the DFT does. That's
So just
pretty much
put
it.
all it in, put all that stuff in hit
Yeah.
play, I guess.
Yeah,
Spits back.
pretty much.
Cool.
All right, so anything else on DFT?
You're a very good teacher.
Nah. I'm lost as well, honestly. I don't go into details because I don't know it either. Alright, so molecular dynamics, as I mentioned, this is simulation for time evolution of the system. So
Is it based on Brownian motion? Molecular, is it same as like fluid mechanics or is kind of different?
well, Brownian motion is a random motion,
Mhm.
but here we have all these appropriate forces that are assigned to the system, so it's not necessarily random.
Okay.
Yeah. So MD is pretty much solving Newton's equations of motion for a molecular system, which is F equals ma. And that is the negative gradient of potential energy. So, I think I mentioned earlier about the connection between DFT and MD. Is that, so if you think about it, there's a simulation box. You have all these molecules floating, and I want to see, it's not going to be in this unit, but I want to see how this system is going to look like in 5 seconds. But I can't just draw these molecules in a box and press click, like nothing's going to happen. Like, we need to know like what kind of forces are being applied between the two, the overall like van der Waals, Coulombic, like everything. And that's called force field, and that's one of the things I think he's gonna ask. Because in the previous papers, on every computation paper, he asked for definition of force field. So know this. So force fields are a set of equations that describe forces being applied on the system. Maybe there's a better definition, so don't trust me. Yeah, but that's the idea.
Can you repeat that one more time?
Set of equations.
Describe force applied on the system.
Yeah. So, those force fields can only come from the DFT calculation. I'll show you why. Because force field, we usually write this as FF. Has two parts, which is bonded bonded interactions and non-bonded interactions. And these, the components are the bonds, angles, torsions, which is the dihedrals, plus the non-bonded parts are Coulombic and van der Waals force. And oh, that's very messy. Give me a second. So, as you can tell, the bond energies come from DFT calculation. The angles, torsions, everything, how they're gonna be located. This part all comes from DFT calculations. So that's why you need to carry out DFT first before you do your MD, unless a proper force field is provided. So yeah, and they come from DFT, and this van der Waals force, I think you guys all know, is related to Lennard-Jones potential. Which is a graph. I think you guys have seen this like many times, like this.
That'd be good.
This graph.
Sweet.
So initially, there's strong repulsion, but as you go on, the attraction kind of cancels it out. So approaches 0. So that's where the Lennard-Jones potential parameter comes in. Yeah, and there is this part where they talk about the ensemble, the canonical ensemble, but I don't think that's that important. But just to let you guys know, there are different types of ensembles. So there is micro-canonical, canonical, isothermal, and grand canonical. So before I go in, ensemble is pretty much a set. It's a set of copies of a system, and each copy represents the microstate of the system, and the average of them all is a good approximation for the average of a macro system. That's what it is. But that is NVE. NVT. Well, I don't think this is important, just you guys don't really need to write this down. So these are pretty much what is kept constant in the system. So here, we're keeping the number of moles, volume, energy constant in the system. Here we're keeping moles, volume, temperature constant. That's what it is. And here they chose canonical ensemble. That's what they kind of. That's what they mean. Yeah, and one last thing. Right? Can I raise this or?
Yeah.
Yeah. Good. One last thing is mean square displacement.
Yes.
I think you guys all know this from stats class. But here in a computational work, we use mean square displacement to show the movement and diffusion of particles.
Diffusion coefficient.
Yeah, that's related to diffusion coefficient. So because here they calculated mean square displacement to compare the diffusion between diffusion onto zinc and diffusion onto the coating material. And we want to say that the diffusion on the coating material is much more favored. That's why they carried out this part. So mean square displacement.
The yellow line is higher, and that means more diffusion. Yeah.
You know, they say.
What are you laughing at?
That's just an equation that you guys also saw from stats class. From this, using Einstein relation, apparently, I don't know this, you can find what you just mentioned, diffusion coefficient, which is where this D is dimension. But I don't think they're gonna ask. They're just gonna ask, why is mean square displacement calculated? Like, what's the meaning of this? Just talk about how this shows the movement and the diffusion of the particles. So from this we can calculate diffusion, and with higher values of this, we're saying that that diffusion is going to be more favored. That's why this was part of the MD simulation. So that's that, and yeah, so if you guys look at page 6, I'm sure all the battery part you guys are familiar with. If you look at page 6, the image C, D, E, F, G, H, these 6 are the MD simulation results. So C and E is pretty much on surface. We simulate all these ions that are shown in pink molecules, and later, and then if you press, click, with zinc surface, it kind of went like this. Whereas with the coating material, it kind of went like that. So we're saying that this is more horizontally deposited from molecular dynamics simulation and how ions are stacked. And from the top view as well, with the coating material, it's more evenly spread out. Yeah, that's what the MD simulation is for. I think that's pretty much it for the computational part. I think with all the battery parts, you guys probably know better than I do. And yeah, that's it for DFT and MD. There are like a lot more, but I think I just kind of talked about what could be asked on the exam. Yeah, that's pretty much it.
Thank you so much.
Of course.
Figure 3B, it's from DFT, right?
Yeah, the Bader charge analysis.
Yeah, that,
Do we
if
have
you
to worry
explain
about
that.
Yeah, the Bader charge analysis, I actually don't know that, so I actually need to have to look into that as well. But
But do you think that's something we need to worry about in terms of the quals, or is that like too in depth?
let me just search up what it is real quick.
It says it's partition the electron density of the system and assign electronic charges to individual atoms.
Hey, can I look at that real quick?
Yeah, I just
Oh,
write
okay.
it down.
Yeah, I know what this is. So this is pretty much wait, isn't this from DFT calculation?
I think so.
Yeah, so from the DFT calculation, you can also show that, you know, even in a water molecule, it's a polar molecule, so some parts gonna be more negative, some parts gonna be more positive. And from DFT, you can show how these charges are spread out in a molecule. So to show which part is relatively more negative. And from that, we can also kind of assume, oh, this part is going to be the site for binding, if that's more favorable in a electrochemical manner, kind of like that. So I think that's why they. So that just shows the distribution of charges in a molecule.
Okay.
Yeah. Yeah, that's. So some of the questions I thought he might ask was first, compare between ab initio and DFT, which I said ab initio is solving the wave function, DFT is solving the electron density. But they both derive from quantum mechanics.
Right. So I guess my question is this: saying that this ab initio thing is within DFT. So how would you?
DFT came about to solve ab initio.
Right.
And
Because it says it kind of like the way it's worded, it kind of sounds like they did both, which obviously isn't the case. It's just the wording is a little confusing.
I think the ab initio comes from the name of the software, right?
Okay, it's not. They're not actually doing ab initio.
Yeah, it's just the name of the software.
Okay,
I
but
think,
they're
yeah.
not doing ab
No,
initio.
no.
Okay, thank you. That's helpful.
So, I know. So, like, as far as I know, there's no computer right now that can solve ab initio. Like, that's impossible.
Because it's solved directly.
It's way too complicated.
No, I saw
You're
one.
solving for each electron, and that does not really make sense. And DFT kind of gives you a route for you to actually calculate that, which is treating the electron cloud density of the molecule. Second is comparing between DFT and MD and how they're related. So, one thing I need to tell you guys: DFT, the smallest unit in the simulation is electron.
Okay.
In MD, smallest unit is the atom. So in MD, we don't think about the electrons. We only think about the movement of the atom. And there's no bond forming or breaking in MD. We just look at how atoms or molecules just kind of interact with each other and how they're going to move around.
So the smallest
An
units
atom.
is electron and DFT. So do we have bigger units? I mean,
What do you mean bigger unit?
Yeah,
you mentioned
yes.
the smallest unit is electron,
Mhm.
and in MD is atom. So
Correct.
in MD, I'm sure that we can simulate molecules which are bigger than atoms.
Mhm.
But what about in DFT? So DFT dealing with electrons always?
Yeah, it's always about electrons.
Always
Yeah,
electrons.
yeah. One and third question is asking the force field. But force field, I know he's gonna ask. He will ask, so know this definition. And I think if you know how to compare between those three, like ab initio, DFT, MD, and how to define force field, I think you will pass this paper, honestly.
Okay, so
There's no way he's gonna go deeper than that. Like,
Love that.
At least
Like-
for the DFT stuff.
So
For the paper almost, I think.
okay, so he won't ask from the paper experiment to.
No, I know that he's gonna ask some stuff on the paper as well, but
Okay.
I think that is it's pretty much straightforward. And I know from his last papers, I know he doesn't ask like details of papers. He kind of wants to know if you understood the overall like objective of the paper and how each experiment like DFT MD and mean square displacement, how are they related to what you're trying to find in the paper. So if you know the overall flow and why each experiment's there, I think that's what he's going to ask for the paper part of the paper. But for the computational, these questions should probably be good too. Yeah.
Did you say the second question was comparing DFT versus MD?
Yeah.
And then we landed on the smallest unit being the electron for DFT versus the atom for MD. And DFT is just like a single instant lowest energy versus MD is a time-dependent movement of molecules. Is there anything else, major differences between them
It's a
that
concept.
I'm missing?
Okay.
Other than
can't
MD also
yeah.
requires DFT to get
But
the
it
force
can't
field.
be
to go.
applied.
Right.
Like,
And also
and
just
no one
to
can solve it or use it.
this is a controversial part. The fact that MD is time evolutional simulation, you cannot assume that this is not going to be time evolutional. This can be. It's just that the computers that are available at this point cannot calculate DFT in a time evolutional manner.
Okay.
That is just gonna melt your CPU. Like that does not make sense. So don't say this is time evolutional, this is not, because in the future this could be. Like you never know. So so it's much safer to talk about how this is solving for wave functions. And if you talk about wave functions, it has to be about electrons. So the units are in electrons, whereas there's no bond breaking forming. The smallest unit is atom, and this solves for Newton's second law about forces and how they're related. You need your force field for MD simulation, and that comes from your DFT results. I think that's a solid explanation, and he'll give you a mark for that for sure. He might be asking, what is a mean square displacement, and how is that even related to this paper?
Okay.
Like diffusion, the movement of particles. I think that should be it. That's yeah. I know most of you guys thought this was McDowell's paper, and unfortunately it wasn't. It's all about like simulation, but if you know these basics I just told you, I think that's all he's gonna ask. Yeah.
Awesome, thank you.
Yeah, of
Thank
course.
you.
I feel like we should clap.
So much.
I'm sorry. That was so helpful.
So, any of you guys doing the catalyst paper as well?
Yeah.
Yeah.
If you wanna.
No. If you know DFT, that's a very easy paper. They also talk about, so you know how they talk about the most favored oxygen, I guess, structure at every temperature and every pressure for anything. And that is solved by DFT because that simulation tells you the lowest possible state energy at that system. That's why they use DFT to solve for that each point, and they see, oh, at lower temperature, like FCC is favored. So they just compare the energy values from DFT and just go for the lowest one, and they just say that's the most favored one. That's how they approach it. So that should be an easy paper for you guys as well. Yeah.
Do you think any more like DFT knowledge should be known for the silver paper other than what we just went over, or no?
No, and I'm thinking this is Professor John's paper, this zinc paper, and that I'm thinking it's Professor Rampy, and I know from past papers, he actually doesn't ask much about DFT. He asks more about the paper itself.
Okay.
So
Does he ask about thermo a lot, or?
I think he does. I think he does.
Cool. So we'll have to actually
Yeah,
rewrite that equation probably.
So
That one. I'm assuming.
this DFT knowledge is gonna be more than enough for that paper, I think.
Cool.
Yeah.
But this is also similar to the other one that we had atoms, you know, the absorption on the surface. It's
Yeah.
very similar to that one.
Yeah.
Surface energy, this stuff.
Mm-hmm.
It's a lot like the growth papers.
Yeah, it
Gallium
is.
nitride and the WSU2.
Yep. We're all
He's
very
thinking
similar.
gonna ask chemical potential.
Yeah.
Those don't have DFT.
What? They have simulation stuff.
But not DFT. That's molecular. That'd be kinetics.
So they already add in. They add. Where do they get the energies from?
Is that it? Okay.
Are we good?
Maybe
Yeah,
DFT,
we're done.
but they
We're
don't
done.
actually